Hello and welcome to our next lecture. This lecture today is going to be on what's called predicate logic, which is the next extension to what we talked about before, propositional logic. I guess exactly we can make the following definition. So first I'll write the title. So we have predicate logic. This is going to be very strongly based on propositional logic, and really any statement in mathematics can be written in terms of predicate logic once you've built up the proper theory, the correct mathematical theory. And generally speaking, that theory that you need to solve and develop a given mathematical theorem is set theory. Set theory is actually built from predicate logic. Predicate logic is really the best starting place. There are other ways of doing this, but by far the most common is developing a system of predicate logic and following those rules very rigorously. So this is how we do it. And in the exact definition of a predicate is as follows. We'll see exactly what this is. So we see that a predicate, or sometimes called a propositional relation or function, is itself a proposition which depends on the truth value of one or many input propositions. Truth value. One, and I'll put in parentheses, or many input propositions. So we defined what propositions were in the last lecture. And the idea now is that we say that a predicate is a statement that depends on the truth or false value of some input proposition. It could either be true or false. So it's also a proposition, but now this is a proposition whose truth value really just depends on whatever the input proposition is. So for instance, when I write down our notation for this, typically could be something like P of X, where X is some input proposition and or some proposition that depends on X. Right, so the truth value of P depends on the truth value of this input proposition. You can also talk about the value of the input proposition, but it depends on whatever X or Y is. And this is a nice thing, because we can think of this as being, we can have a proposition, we'll call it Q maybe, or sorry, a predicate Q of X and Y. This is a predicate that depends on X and Y. So it's a propositional relation or function that depends on both X and Y. You could have some R. It depends on three things: R of X, Y, Z. And let's say, for instance, like I have a proposition or a predicate P, which is a propositional function of X, so one thing, and a predicate Q, which is a propositional function of two things. I could maybe then what if I maybe want to define the proposition of X, Y, Z as being built up from, and this dot dot with the by implication sign right here sometimes means that we can define a predicate of like these three variables maybe as P of X, and we say maybe the and operation between this and Q of YZ. Right, this is just one example of how flexible this really is in terms of actually constructing new proposition or new propositional functions or new predicate relationships. So the idea and the reason that we're doing this is that while the propositional calculus has gotten us to a certain point in terms of being able to deal with propositional statements, so finitely many propositions. So for instance, like up until now, we can deal with propositional calculus. Allows us to deal with up to finitely many propositions. So for instance, I could have like P1, P2 to Pn. We know that we proved De Morgan's laws last lecture, so let's say I want to do maybe the knot of P1 and P2. We know that this is the same thing as not P1 or not P2. We proved this logical equivalence last lecture. We sometimes want to construct these propositions, these individual propositions, using more than just finitely many elements. Or I might have a proposition that depends on more than finitely many elements, so infinitely many elements or infinitely many propositions. And the idea is that I can't do that with just this propositional logic that we've developed up to this point. We have to extend this to a little bit and define a little bit more in terms of what's called predicated logic. Now, this is going to allow us to deal with general statements that don't depend on the number of elements or the number of input propositions. So while this is good, propositional logic is good. It's very, very good for finitely many propositions. We need to develop some new a new logical system for infinitely many, or allowing for the possibility of infinitely many input propositions. But we're going to do it very, very similar to how we do normal propositional logic. So predicated logic is going to be very similar in some sense to the propositional logic, but it's not exactly the same because we have to be a little bit more general. So the next definition that we're going to have is the following, and really this is like a definition / notation. So we're going to first let p of x be a predicate or predicated function. And we're going to define the following symbol. So this symbol right here denotes a very specific proposition. So we're going to let this symbol right here denote a very specific proposition. And specifically, this proposition is going to be the following statement. So the symbol with it's an upside down A right here, x p of x. This always stands for the statement for all x p of x. Or even if you want to be a little bit more specific, you can say for all x statement p of x, because we know that p of x itself is a proposition. So for all x statement P of x. And what that means is the following. It means that I can say, if I write down, say, that P of x is the proposition. I don't know. We'll try this right here. P of x. So this is a good example just to kind of explain what I mean. P of x is the proposition x greater than 1. All right. Then what we can talk about is the following. We can say that. For all x, P of x is the proposition for all x is greater than 1. So it essentially it encapsulates the idea of saying for all x, the statement P of x, whatever that statement is. So this is a good example right here. But there's a lot of other examples as well in the book that you should look through as you go through the book. We're up to around 1.4 in the book, and hopefully by the end of this lecture we'll get to around 1.5 in the book. So we're about halfway through chapter 1. I'll post a video a little bit later on with a number of different examples where I explain examples from the previous chapters, so that you can kind of see not just the theory of what we're doing here with propositional and predicate logic, but also how to use it in terms of constructing statements and whatnot. But this right here is called the proposition. As a proposition, it's called the universal quantifier. So this symbol right here, this proposition, and I can change this a little bit right here. So specifically, this symbol is going to denote the proposition, proposition known as the we'll call it the universal quantifier, because this is exactly what it's called. So we'll say the universal quantifier proposition. And statements like these are used very often in mathematics. We always will be using these universal quantifiers to describe a property of some element in some set. And as of this point, we haven't yet defined what it means to be a set. Set theory is actually defined based on this propositional logic. But the idea is that we have to first start with propositional logic and sort of build our machinery for propositional logic in order to correctly define set theory and kind of really create a lot of the ideas in modern mathematics. But so this is the universal quantifier. The universal quantifier is a very, very important thing to understand and use. It's always, we'll be using this a lot in mathematics, and just as important is in some sense, it's not the opposite of the universal quantifier, but it's related to the opposite of the universal quantifier in a very specific sense. By the way, what we can do is we can also, I'll give you another example as well. We can think of the universal quantifier as almost like in the intersection operation. So if I do a universal quantifier on, say I have finitely many propositions, so P1, P2 to Pn. So this reduces to the case of finitely many propositions. If I write down the statement for all I, Pi, this is the same thing as saying P1 and P2 and P3 and P4 and so on and so forth, all the way to and Pn. So when you have finitely many propositions, this for all quantifier is really just an intersection argument. It breaks down to predicate logic. But what's very nice about this in this construction, this for all construction, is that we don't specify here what x is. And in some sense, that gives us power. It might look confusing to the beginning mathematician, because very often when you're writing down a statement, you need to. It's one of the most important things is specifying the domain, the set that thing falls into. But the thing with predicate logic and propositional logic is that we're kind of removing ourselves a little bit from that. We need to do predicate logic before we can define what a set is. First we define predicate logic, and then we build up the concept of a set, a mathematical set, from predicate logic. So this is just an important commentary. But so if we continue down the notes, we get to our next definition, which is almost as important as the universal quantifier, and this is what's called the existential quantifier. So we say, let P of x be a predicate and we define the symbol the following symbol to be the existential quantifier. So we backwards E is like up here for the universal quantifier we put an upside down A. Here for the existential quantifier we put a backwards E. We put x P of x. And sometimes you'll see me also write a colon here just to be specific. You can do it for the existential and for the universal. You don't need the colon, but it is kind of a common thing to sometimes reverse and put this colon here, separating the quantifier symbol from the actual predicate symbol itself. So it's not necessary, but I do recommend it. So we define the existential quantifier to be logically equivalent to, or the same thing as what's called the statement, there exists at least one, possibly more, x such that statement P of x is true. So, or such that statement P of x. And almost immediately what you should be able to notice is that this is like the generalization of the OR operation. So for if we kind of go to finitely many, we look at the case of finitely many propositions, P1, P2, P3, just like we did up here. So in this example right here, I'll just do it right here. So P1, P2, P3 to Pn, just like before. If I do there exists I such that P of I, or Pi, right, this is the same thing as saying P1 or P2 or P3 or all the way to an OR of Pn. It's the OR statement between these n propositions that we started with. This is what it is for finitely many propositions, but the nice thing about this notation down here is just like before, we don't reference how many x's there are, so we can really have x be infinitely many, uncountably infinitely many. This is a concept that we'll talk about when we get to countability and set theory a little bit later. But this is very powerful because we don't specify exactly what x is. We leave that for until a little bit later when we actually kind of pin down exactly what set it is. So just like we have De Morgan's laws as well, this is the next idea here. We have a very fundamental relationship between universal quantifiers, and this is can kind of be hinted at when you take the negation of this statement right here, say, or the negation of this statement right here. We know from De Morgan's laws for finitely many propositions that if I take the negation of this statement right here, I get the union of the negation of each individual statement, And likewise, this is the same thing for the negation of this there exists statement. But this is something that holds in general, and it works extremely well in general between the there exists p of x. We have a general De Morgan's law for this existential quantifier. So if I write down the statement, there exists x such that p of x, so this, you can read this as, this is the same thing, and it can actually be defined as, if you want to define it as the negation of the statement, so the negative of the statement, the opposite of the statement, for all x, p of x is not true. Or for all x, not p of x. We have to take the negation of that, because if this can be described and proved in a number of different ways, but the main reading here is just to think of this as, this says there exists in x such that p of x, statement p of x is true. Well, this is the same thing as saying that it's not true, that for all x, p of x is not true. These two things are the opposite of one another. These two things right here are the same thing as one another, because the statement for all x, p of x is not true, which is a statement in parentheses right here, this big parentheses. The opposite of that statement is a statement that there exists at least one x such that p of x is true. So this definition makes a lot of sense. And likewise, we have a very similar relation, and we can show a very similar relation between the for all statement. The for all statement's relationship to this there exists statement is that for all x, p of x is the same statement that it's the negation of there exists in x such that p of x is not true. So if there exists in x such that p of x is not true, the opposite of that is that for all x, p of x is true. So this really makes a lot of sense, and this relationship between universal quantifiers is called, it's sometimes called De Morgan's laws for universal quantifiers, because really it's just based on De Morgan's laws for propositions, but now this is like De Morgan's law for predicates. So it's a very, very powerful idea that is extremely useful, and we'll see at least some examples in the class and in the homework of how useful this is, really. So the idea here is that we want to take this idea now and kind of construct certain mathematical sets, or sorry, not mathematical sets, mathematical ideas and mathematical systems, axiomatic systems from basic logic, and really kind of figure out how to prove and make a proof in some given axiomatic system. So that's kind of what we're working towards by the end of this first section. So what we're going to do is I'll add another page here and kind of continue on with the examples and these notes. So a very important remark about these quantifiers is that the order of quantification matters. Just like the order of intersections versus unions matters when you look at the unions of propositions. You got to be very, very careful about what you mean in terms of when you're chaining together these propositions. So for instance, I guess the example that I can use is, let's just say we have a given predicate function, or a given predicated function, p of xy. Just assume p of xy is a predicated function, or a predicate for short. Well, the statement this statement right here reads, if I were to write it down, as there exists at least one y such that for all x, p of xy, statement p of xy is true. There's one way of reading this statement right here, which says that there exists at least one y such that for any value of x, p of xy is true. This is a completely different statement. It's not the same thing. So this statement right here is different from the statement for all x there exists a y such that p of xy is true. Right? This is the same statement as for all x there exists at least one y such that statement p of xy is true. These are two fundamentally different statements. This first statement is implying that we can find at least one y such that for any value of x I choose, no matter what, p of xy, the statement p of xy is true. This is a completely different statement than this statement right here, because this statement right here is saying that for all x, so for any value of x you choose, there exists at least one y such that p of xy is true. So this is saying that for any value of x I can find at least one value of y that makes this true. This is saying right here that there exists at least one y that I can find such that for any value of x this thing is true right here. This makes it should, when you're reading this, make a lot of sense that these two things are different statements, because this is implying the existence of at least one y such that this becomes true for any value of x I choose. This statement is saying something completely different. It's saying that for any value of x I choose, I can find a value of y. So I guess in some sense this is implying the existence of one y that works for all values of x. This is implying that for any value of x I can find at least one value of y. But the idea is that the value of y doesn't have to be the same for each value of x. This is just saying for every single value of x I can find at least one value of y such that this thing is true. It works. So these are completely different statements, and I guess to see this in like a very good example, it's not a very complex example, but it is a good example. You can take the following predicate, choose p of xy to be the predicate x plus y equals 0, where x and y are real numbers. We have to assume that we know what the real numbers are. We don't yet. We haven't defined them yet, but it's kind of hard to do examples without first having access to real numbers. So we just assume that x and y are real. Well, the statement for all x there exists y such that x plus y equals 0 is a tautology. This is a true statement no matter what. If x and y are real numbers, it's a tautology, because what it's saying is that for every x I can find a y such that x plus y equals 0, and that for that y is exactly equal to negative x in the real numbers. The real numbers include the negative versions of the real numbers. So for any real number you choose, I can find the additive inverse of that negative number. This is exactly what, it's a property of the natural numbers, that there's always an additive inverse in the natural numbers, the real numbers. So for example, if I choose that, if I say that x is equal to pi, or 3.14, 159, etc., then y here is going to be equal to negative pi, or negative 3.14 159. And when I add these two things together, I get 0. Therefore, this statement is true. But the preceding, or I should say the reverse statement, if I reverse the order of quantifiers, this is not a true statement. That there exists a y such that for all x, x plus y equals 0. This is not true. It's not true because for any value of y you choose, or like for any value of y you choose in the real numbers as your potential value of y. So we need to find one y right here that satisfies for any value of x, x plus y equals 0. So let's say, for instance, just for example, we found that y. Choose x to be equal to y plus 1, and what you get is the statement that x plus y, this y is supposedly the inverse. It has to be the algebraic inverse of x. Well, this is equal to y plus 1 plus y, which is 2y plus 1, which is not 0. So the idea here is that you can always find a counterexample. For any value of y that you choose, you'll have any number of valid counterexamples that make this a false statement right here. You can never find one real number such that for any other real number, when you add them together, you get 0. There'll always be another real number that doesn't satisfy that. So the fundamental thing here is that these two things are not logically equivalent. They're opposite. They're in some sense not. They're not opposite, but they're different logical statements. So one of the things that you may have noticed is that the existential quantifier, it kind of takes in all the possibilities in terms of we can have the existence of one or many propositions that satisfy whatever the proposition that we're doing the existential quantifier on. Right. That's why in the existential quantifier definition we have that there exists at least one or possibly more values that satisfy the proposition. So we can go a step further. We can actually define what's called the unique quantifier. There exists, what this stands for, there exists the backwards e with an exclamation point. Then we have x, p of x. There's another definition right here, and you can say notation or definition if you want, but it's this means that there exists one and only one x such that statement p of x is true. So this is kind of a very, very important thing, and I'll actually even this is in some sense logically equivalent here instead of equals. I always want to use the 3 lines for logical equivalence because that's something that we've defined previously. So as we go through, we can go through and say exactly define this logically and say that this is the same thing, or it can be defined as, in terms of logical operations, the statement that there exists x and x such that p of x but then we also have to restrict this in the sense that, so we have to say and for all y, for all z, we have that the implication p of y and p of z imply that y is equal to z. Right, this is a necessary extension, or a necessary way to one way. It's not necessary. It's one way of defining the existential quantifier, the uniqueness quantifier. So the existential quantifier in terms of a uniqueness, we say that there exists in X such that P of X, this needs to be true, and for any two values, Y and Z, if P of Y and P of Z are true, then Y has to be the same thing as Z. They have to be equal to one another. So this is one possible way of defining this uniqueness quantifier. The uniqueness quantifier for there exists uniquely some element that satisfies the statement P of X. We have other ways of doing this as well. This isn't the only way, and this is one of the nice things about propositional logic. Sometimes there's a simpler way of writing something down. For instance, I could write down for this, I could also define this as follows. It's a slightly different term. We have to say that there exists an X such that for all Y, if P of Y is satisfied, so P of Y is true, then X equals Y. But we also have to have the reverse implication as well. If X equals Y, then P of Y is satisfied. So this needs to be not an implication, but a by implication. And this is another way of writing down. So this definition up here only involves the implication operator. This definition down here involves the by implication operator, but it's slightly shorter than this definition up here for uniqueness. So this is kind of a very nice idea. It's basically saying that there exists some element X that satisfies P of X, but it's the only element that satisfies it. And this is a huge concept in mathematics. The concept of uniqueness of an object, or uniqueness of an element in a set, uniqueness of a solution. So for instance, like when you go to solve certain equations in algebra or in calculus, when you're solving for certain solutions to functions, so, a good example is differential equations. You got to prove uniqueness of differential equations. This quantifier is really important because a lot of times you want to show that there exists one and only one solution to a given equation. You need to know how to write it down in terms of like strict logic, actual predicate logic, and that's why this is kind of a very important thing to do, and know how to do. So this is the definition of the uniqueness quantifier. And the last thing that I want to talk about today is how to negate more and more complex statements, so more and more complexified statements. And this is as simple as just using the definitions from before, the way that we've defined the relationship between the negation of a for all statement, so the negation of a universal quantifier versus the negation of an existential. And it's really just applying those general De Morgan's laws that I talked about earlier. So for instance, if I were to write down the statement, for instance, let's say our statement is the statement: for all X, there exists a Y such that for all Z, Q of X and R of YZ. Just say, for instance, this is what we have. And again, like I said, you can put the colons here if you want to kind of just denote that for all X, there exists a Y such that for all Z, this statement is true. So the statement Q of X and R of YZ is a true statement. In order to properly negate this statement, like the negative of this statement, we have to go through and use our reverse De Morgan. You can think of them as the existential and universal quantifier De Morgan's laws. So more the general De Morgan's laws for each one of these input statements, because we know that in general, right, we have that the negation. Well, I'll just do it in terms of the quantifiers, that the for all X P of X is logically equivalent to the negation of there exists in X such that not P of X is true. Well, this is the same thing as saying the negation of for all X P of X is logically equivalent to there exists in X such that not P of X is true, or P of X is not true. For the exact same reason, in our definition, there exists in X P of X. The relationship to this is that we have there exists in X such that P of X is the exact same thing as not for all X, not P of X, which means that the negation of a there exists statement, the negation of there exists in X such that P of X is logically equivalent to the statement for all X, not P of X. So using this idea, then, one of the things that we can do, which is really, really nice, is that we can say, apply this multiple times. We know that the negation of this long statement right here, this long universal quantifier, is the exact same thing as the statement there exists in X, which is the negation of this, such that for all Y, such that there exists a Z, because the negation of for all is that there exists. Got to be careful here now too, because this now needs to be the negation of this statement. So I'm going to put here the negation of the statement Q of X and R of YZ. This is the same thing as there exists in X such that for all Y there exists a Z such that, and I can even use this is just a proposition here, so I can use my normal De Morgan's law to write not Q of X or not R of YZ on my negation of this statement right here. And this gives me exactly, this statement right here is the negative of this statement that I started with right here. So that the opposite of the statement for all X there exists a Y such that for all Z Q of X and R of YZ is true. That statement is negated by the statement there exists in X such that for all Y there exists a Z such that either not Q of X is true, so not Q of X is not true, or not R of YZ is true. That's the opposite of the statement we started with. So this may seem like an unnecessarily complicated exercise, but the point here is hopefully that you can see that every single statement in mathematics, any statement that you want to make at all in any mathematics or computer science or any theorem that you might write down, is constructed like this. So the idea here is that we now have a beautiful language that we can use to describe any statement that we want, any theorem that we want, any statement that we want, in terms of these predicated statements. And to end this lecture, what I'm going to do is go over one of my personal favorite examples, and you can really pick any example that you want in mathematics and rewrite it using this predicate logic. This is really like the fundamental building blocks, like I keep saying, of any mathematical theorem. But the example that I want to choose comes from somewhere that I'm hoping that most people have a little bit of familiarity with. I'm hoping that everyone in the class has had a background in Calculus 1. And even if you haven't had Calculus 1, that's okay. I can still explain this example and teach you what you need to know about this example. But this property is what's called the property of continuity of a function. We want to write this down, but write it down definitively in terms of just predicates and quantifiers. So this is what we'll do right here. I'm gonna draw two axes, so an axis for X and an axis for Y. The other way around. This is my axis for X, and this is my axis for Y. And I want to write down the mathematical definition for continuity first off. So this is X naught, say. The Y value here we'll call f of X naught. So this is my Y value here. I guess first I want to explain why the definition of continuity is the way it is for a function. And then I want to explain how that definition can be used to get the negation of it. Directly using just logical operations. So the idea is that we're going to... what I'm doing here is I want to describe and I guess define what it means. So the definition of continuity of a function. So this function right here we call y equals f of x. And typically in a calculus 1 class, you'll see that continuity of a function y equals f of x is the same thing as the following proposition. It's the proposition that the limit as x approaches x naught of the function f of x equals the value of the function at x naught. Like in this picture right here. In this picture, you see exactly what I'm talking about. There's the the black dot right there is the value of the function f of x naught, and you can see very clearly, hopefully, from this picture that the limit from the left is approaching this value. So this function in this picture is very clearly continuous. I can draw this graph without lifting my pencil off the page. The idea is that this though it can still be unpacked a little bit more, so to speak. Like this is nice in terms of a calculus 1 definition, but it's not nice in terms of the most general definition. It doesn't work in some sense in terms of a very general definition. Intuitively, it tells you what everything that you need here. It tells you that in order for the limit to exist, you need the value of the function to exist at the point, and you need the limit to... So in order for the function to be continuous, you need the value of the function to exist at the point x naught, and you need the limit from both sides to exist at the point x naught. So the limit from the left has to exist, and the limit from the right has to exist, and they have to be equal. So that's what this is right here, and that's what this is right here. We want to write this down exactly in terms of just exact mathematical logic, so propositional statements. And it took mathematicians years and years and years to figure this out. It wasn't just figured out overnight, but the idea is that any statement in mathematics should be able to be rewritten in terms of just predicates and quantifiers. And it turns out that this can be, in a very, very nice way, rewritten in terms of predicates and quantifiers. So what I'm first going to do is I'll write down the exact definition and sort of explain it a little bit, and then I'll sort of rewrite that definition in terms of very, very short predicates and quantifiers. And what I'll end with is showing that directly from the definition of continuity of a function, we can find the definition of discontinuity of a function, what it means for a function to be discontinuous, by taking the negation, the exact logical negation of the definition for continuity. So the exact mathematical definition of continuity at a point x naught is the following. We have that we say that it's the statement for all values of epsilon greater than 0. Now what epsilon is I'll use green up here. Epsilon is sort of like, you can think of it as like a tube surrounding the value of the function. So for instance, like this value right here, this line right here, this straight line going across, is at f of x naught plus epsilon. And this value right here is at f of x naught minus epsilon. So any point, any y value in this epsilon tube is within a distance of epsilon from f of x naught. And this is the statement for all epsilon greater than 0. Well, that means that I can bring this value of epsilon as close as I want to the value of the function. So I can sort of shrink this tube and bring this tube down and bring this tube up right here to shrink this tube as close as I want to the value of the function. So it's for all values of epsilon greater than 0, there exists at least one, possibly more. I'm just going to put there exists a delta greater than 0. I'll draw the delta. I'll draw one possible delta in blue down here. So I'll draw, this is a delta that works. Or this right here is x naught plus delta. This is x naught minus delta. So for all epsilon greater than 0, there exists a delta greater than 0, such that we have the following implication. If x minus x naught is less than delta, so if x, like is right here maybe, inside this delta tube, then the value of the function f of x is inside the epsilon tube. It has to be trapped inside the epsilon tube. This is what it means in terms of just equations, but this is saying if x is inside the delta tube, or x minus x naught is less than delta, then we also have to have that the value of f of x, in this case right here, this is our f of x, this has to be within the epsilon tube. So this statement is a very, very nice statement, and it's a statement that is in some sense a little bit more advanced than this statement right here, but these two things mean the same thing. You can say that this proposition right here is the same thing as this proposition right here, but this proposition down here that is the more correct definition of continuity, because of the fact that we can express this now directly in terms of universal and existential quantifiers, because this statement now can be rewritten even in a more compact version as for all epsilon, if epsilon are all positive numbers, there exists a delta such that the statement, and this depends on epsilon and delta, really. It also in some sense depends on x and x naught, just like before. So that will kind of, you can generalize these ideas, but we're just going to put p. You have the implication p of delta implies the implication q of epsilon. We'll call this thing right here, the statement x minus x naught less than delta, p of delta, and we'll call this statement right here q of epsilon. So f of x minus f of x naught is less than epsilon. This right here is the mathematical definition of continuity. If we define p of delta as the statement x minus x naught is less than delta, and we define q of epsilon as a statement f of x minus f of x naught is less than epsilon. This right here is the mathematical definition of continuity, which is expressed as exactly like before in terms of predicate logic. So in terms of this universal quantifier in epsilon and this existential quantifier in delta. It's a really, really nice idea. So it's written in some sense as nicely as this definition up here, but now we can use all of our rules from predicate logic and propositional logic. So remember before, we're going to use this as a result a lot in the class. So last lecture I proved that the statement P, if P then Q, so if P then Q is logically equivalent to the statement not P or Q. And then I also showed that using these logical equivalences, you can, without even going to truth tables, if I want to find not if P then Q, well, this is the same thing as we first applied. It's not P or Q, which is the same thing as not P and not Q. This is from De Morgan's law, which is the same thing as P and not Q. So we have that this statement right here we showed was logically equivalent to this statement right here. So what this means is that if this is the definition of continuity of the function, And the definition of discontinuity of a function is the negation, or should be, this should be the same thing as the negation. So discontinuity, we'll put it this right here, is the same, should be the same thing as the negation of continuity. And this is exactly what we see. So that the definition of discontinuity is the negation of this statement right here. The negation of this statement right here ends up giving us the following, or should end up giving us the following. You have the negation of this right here, which is a there exists statement. So the negation of the for all epsilon becomes a there exists statement. So there exists an epsilon such that for all delta, you have to negate this, you have to negate this, and then we have to take the negation of if p then q. So if p of delta, then q of epsilon, which we just showed up here, and we showed this last lecture, that the negation of if p then q is the same thing as p and not q. So we have that the definition of discontinuity is the statement there exists an epsilon such that for all delta, you have p of delta is, remember, x minus x naught is less than delta. So this statement, this is our p of delta, and we have to have not q of epsilon. So not q of epsilon is the statement that f of x minus f of x naught is greater than or equal to epsilon. So we have to have that this is not q of epsilon. So f of x minus f of x naught in absolute value is greater than or equal to epsilon. And this makes an unbelievable amount of sense, a super big amount of sense. And at first you might not be able to see that, but we'll see it directly by looking at just an example of a discontinuous function. So let's kind of draw a picture of a discontinuous function and see that this negation right here is in fact the correct definition of discontinuity. So we go x naught here, but some value, this is our value of the function right here, and it has to be discontinuous, so we have to have some sort of jump in it. We'll put it right here. And what this is saying is that there exists some value of epsilon, so there should exist some value of epsilon, possibly many values of epsilon, and there are many, but I'll just choose a value of epsilon that's very nice for this picture right here. This is one value of epsilon that works. So there exists a value of epsilon such that for all delta, so for any value of delta that I choose, no matter how close I want to get, how small it is, and you can always choose a delta smaller if you want to. This is x naught plus delta, x naught minus delta. This value right here is, remember, this right here is our f of x. So this top value is f of x naught plus epsilon. This lower value is f of x naught minus epsilon. And this value right here is f of x naught. So we have that there exists an epsilon, at least one, possibly more epsilons, such that for all delta, no matter what size delta is or how small delta is, we have that x minus x naught is less than delta. So we have points here, x minus x naught is less than delta. Any point in here, we have that x minus x naught is less than delta. And f of x minus x naught is greater than or equal to epsilon. And this is where we get the violation of our continuity condition. And this is true right here. For any of these points x right here, this point right here, this point right here, no matter how close you want to get to the discontinuity, this is always going to happen. You're going to have points x that are outside of your epsilon tube, which is this condition right here. So this is why this is the correct definition of discontinuity for our function, and we obtained it directly from the definition of continuity of a function without even using any calculus at all. We just used our basic laws of logic. This is a very, very powerful tool. This means that if we can correctly write down mathematics and mathematical theorems using this basic predicate logic and propositional logic, so it's a combination of predicate and propositional logic, then when all else fails, we can always resort to using this logic, the logical rules, to argue within the system of axioms that we're working in. So this is a huge idea. But what we'll do next lecture. So this is done. This is it for this lecture. Thank you for tuning in and watching this lecture. I hope this kind of helps with your reading and with your studying. But the next lecture that I want to talk about, I'll define what I mean by an axiomatic system in the theory of proofs. So we'll start talking about exactly how to construct proofs and how to write down proofs and what we actually mean by mathematical proofs. Thank you again for tuning in today, and I hope you have a great day.